Assalamu alaikum and good day everyone. I am Nursada Dundi, first presenter from Group 2, and we will be discussing the Chapter 2, Thermal Property of Matter, understanding how heat and temperature affect matter. Matter behaves differently depending on temperature and energy, affecting properties like pressure, volume, and state. Everyday examples such as boiling water, condensation on a glass, or freezing vapor demonstrate how changes in temperature lead to changes in physical behavior. These observable large-scale or macroscopic properties are closely connected to the microscopic behavior of molecules, including their motion, energy, and interactions. Understanding this relationship helps explain how substances respond under different conditions. By studying both macroscopic properties and microscopic dynamics, we can better understand concepts such as pressure, heat, and phase changes. So, with this report, we'll explore these connections with a focus on thermal properties of matter and how molecular behavior influences what we observe in gases, liquids, and solids. But before we begin, let us first know the learning goals of this chapter. By studying this chapter, students will learn how to relate the pressure, volume, and temperature of a gas, how the interactions between the molecules of a substance determine the properties of the substance, how the pressure and temperature of a gas are related to the kinetic energy of its molecules, how the heat capacities of a gas reveal whether its molecules are rotating or vibrating, and what determines whether a substance is a gas, a liquid, or a solid. I will be discussing the equation of state. So the conditions in which a particular material exists are described by physical quantities such as pressure, volume, temperature, and amount of substance. For example, a tank of oxygen in a welding outfit has a pressure gauge and a label stating its volume. We could add a thermometer and place the tank on a scale to determine its mass. These variables describe the state of the material and are called state variables. The volume V of a substance is usually determined by its pressure, temperature, and amount of substance, described by the mass or number of moles N. Ordinarily, we can change one of these variables without causing a change in another. When the tank of oxygen gets hotter, the pressure increases. If the tank gets too hot, it explodes. In a few cases, the relationship among P, V, T, and M or N is simple enough that we can express it as an equation called the equation of state. So again, equation of state is a mathematical equations that describe the relationship among the variables. And another simple equation of state is the one for an ideal gas. Ideal gas law describes the relationship among pressure, volume, and temperature, and the amount of gas. It assumes that gas particles move randomly, have negligible volume, and experience no intermolecular forces. So in ideal gas law, we have an experiment where scientists study gases using a container with a movable piston. This allows them to change the volume, temperature, and amount of gas, and then measure the pressure. So from the experiments, they discovered three important relationships. First, the volume increases when the amount of gas increases. Second, the volume decreases when the pressure increases. And third, the pressure increases when the temperature increases. So these three relationships are combined into one equation called the ideal gas equation. This equation helps us understand how gases behave under different conditions. However, this model works specifically at low pressure and high temperature because gas particles are far apart and move freely. So the ideal gas law states the pressure, volume, temperature, and amount of gas are related by the equation PV is equals to nRT, where P is pressure, V is volume, N is number of moles, R is gas constant, and T is temperature in Kelvin. The equation combines several simpler gas laws, including Boyle's law, which pressure volume relationship, Charles' law, volume temperature relationship, and Avogadro's law, volume and amount relationship. So because of this, it provides a comprehensive model for understanding how gases respond to changes in their environment. So we have here an example. So what is a volume of a container that holds exactly 1 mole of an ideal gas at standard temperature and pressure, or STP, defined as temperature of 0 degrees Celsius, which is equal to 273.15 Kelvin, and a pressure of 1 atmosphere, which is equivalent to 1.013 times 10 to the 5 pascals. This problem involves the properties of a single state of an ideal gas, so we use the equation PV is equals to nRT. We are given the pressure, temperature, and number of moles. Our target is variable. Our target variable is the corresponding volume V. So from the equation, using R is proportionally constant. The numerical value of R depends on the units of B, V, and T. The current best numerical value of R is equals to 8.314 joules per moles times Kelvin. So here's the solution. V is equals to nRT divide P. So N is 1 mole, R is the gas constant, which is 8.314 joules per mole times Kelvin, and then times temperature, which is 273.15 Kelvin, over the pressure, which is 1.013 times 10 to the 5 pascals, and then we divide it and we can get 0.0224 m cube, or 22.4 liter. But STP, 1 mole of an ideal gas occupies 22.4 liter. This is the volume of a cube, 0.282 meter, or 11.1 inch on a side, or of a sphere, 0.350 meter, or 13.8 inch in diameter. So next we have van der Waals. The van der Waals equation is an improved form of the gas law that accounts for the finite volume of gas molecules and the attractive forces between them. It introduces constant A, which is attractive forces, and B, the molecular volume, which vary for each gas. These corrections make the equation more accurate for real gases, especially at high pressures and low temperatures. However, at low pressure or high temperature, gases behave more ideally, and the van der Waals equation approaches the ideal gas law. So an equation was developed by the 19th century Dutch physicist J.D. van der Waals. The interaction between atoms was named the van der Waals interaction after him. The van der Waals equation is P plus an squared over v squared times v minus v nv b v minus nb is equals to nRT. This equation provides a more realistic description of gas behavior by considering the volume of gas particles and the attractive forces between them. These corrections make it more accurate than the ideal gas law, especially at high pressure and low temperature. Overall, it helps us better understand how real gases behave under conditions where the ideal model no longer applies. And lastly, we have the PV diagram. A PV diagram shows how pressure and volume are related in a gas. Each line on the graph represents a constant temperature, which we call an isotherm. For an ideal gas, the relationship is given by the equation P is equals to nRT over V. This means that as the volume increases, the pressure decreases, as long as the temperature stays the same. As the volume increases, the pressure decreases, forming a hyperbolic curve on the diagram. This behavior reflects how gas particles spread out and collide less frequently with the container walls as the space increases. So in this diagram, it illustrates isotherms for an ideal gas, which are curves representing constant temperature conditions. The graph plots pressure P on the vertical axis against volume V on the horizontal axis. Each curve corresponds to a different temperature, labeled T1, T2, T3, and T4, where T4 is the highest temperature and T1 is the lowest. As temperature increases, the curves shift upward, indicating that for the same volume, the gas exerts a higher pressure at higher temperature. Along each individual curve, pressure and volume are inversely related. This means that as the volume of the gas increases, its pressure decreases, and vice versa. This relationship is described by Boyle's law, which states that pressure is inversely proportional to volume when temperature is held constant. These curves are derived from the ideal gas equation PV is equals to nRT. For a fixed amount of gas, an increase in temperature results in an increase in the product of pressure and volume. This explains why higher temperature isotherms lie above lower temperature ones on the graph. Overall, the diagram demonstrates how pressure, volume, and temperature are interconnected in an ideal gas, and how changes in one variable affect the other under constant temperature conditions. The second diagram shows a pressure versus volume graph for a real or non-ideal gas. So what makes this different from an ideal gas? In an ideal gas, the curves are smooth. Here, the graph includes a flat, curved, shaded region, which shows something special. The gas is changing phase from gas to liquid or liquid to gas. So each curve represents the behavior of the gas at the different temperature. The temperatures are labeled from T1 to T4, with T4 being the highest. One important temperature shown is the critical temperature, or the TC. Above the critical temperature, the gas cannot be turned into a liquid, no matter how much pressure is applied. However, below this temperature, the gas can change into a liquid when compressed. The shaded region in the diagram represents the liquid vapor equilibrium region. In this area, both liquid and gas exist together. As the gas is compressed, instead of the pressure increasing significantly, the gas gradually condenses into a liquid. For temperatures below the critical temperature, the process starts with the gas. As it is compressed, it enters the shaded region where condensation occurs and eventually becomes a liquid. For temperatures above the critical temperature, there is no phase change, and the gas behaves more like an ideal gas. Overall, this diagram shows how real gases behave differently from ideal gases, especially because they can change into liquids under the right conditions. So, in conclusion, the thermal properties of matter explain how heat and temperature influence the behavior of substances. We learned that pressure, volume, and temperature are closely related, as described by the ideal gas law, and that real gases may behave differently under certain conditions. These properties are directly connected to the motion and interaction of molecules, which determine whether a substance exists as a solid, liquid, or gas. So, by understanding both the microscopic behavior of particles and the macroscopic changes we observe, we can better explain everyday phenomena such as heating, cooling, and phase changes.
Assalamualaikum and good day everyone. I am Michaela B. Salik, and for the second lesson we're going to talk about molecular properties of matter. So far in this course we have treated matter as a continuous substance. We have measured its density, its elasticity, and how it expands with temperature. But today we're going to put on our microscope and look at the individual molecules. We want to connect the microscopic world of atoms and molecules to macroscopic properties we can measure in the lab. The key to this connection lies in the understanding the forces between the molecules. So, what is molecular properties of matter? Refers to how the tiny particles like atoms or molecules that make up everything around us determine the behavior of the materials we see and touch. For microscopic properties, what we can see, for instance, is what color, hardness, and whether something is solid or liquid. For molecular properties, why it happens. For instance, how the tiny particles are arranged in how they move. The molecules force and potential energy curves. Intermolecular force, the between neighboring molecules, it is electrical in origin and depends strongly on the distance between the molecules. Potential well, a region where potential energy is at the minimum. A molecule in a potential well requires an input of energy to escape the attractive forces of its neighbors. This graph is the heart of our discussion today. As you can see at the right side, the image on the top. On the top, we see the force between two molecules. Notice the three key regions. When molecules are too close on the left side, the force is repulsive. This is why you can push a solid through another solid. When they are at the equilibrium distance or the RO, or R0, the forces balance. When they are farther apart, they attract each other. Below, we see the potential energy curve. It's related to the force by calculus. This curve forms a potential well. Think of it like a valley. The bottom of the valley at separation zero is the most stable place to be. The depth of this valley is the amount of energy a molecule needs to escape its neighbor's attraction entirely. For the phase transition, the transformation of matter from one state, solid, liquid, or gas, to another driven by changes in temperature or pressure. It occurs when thermal energy. The scenario is low temperature. The condition is kinetic energy less than the binding energy. So, what is the molecular behavior behind it? Molecules lack energy to overcome attractive forces. They remain bound to neighbors, vibrating around fixed positions like solid or sliding past each other like liquid. The phase of this scenario is solid or liquid. For the scenario of high temperature, kinetic energy is greater than the binding energy. So the molecular behavior behind it is molecules gain enough kinetic energy to overcome the potential well. They break free from intermolecular attractions and move independently. And the phase of this scenario is gas. And this is the key takeaway. Temperature is a measure of the average kinetic energy of molecules. Think of it as the energy of motion. The depth of the potential well, or the U0, is the binding energy. The energy holding molecules together. The pace of matter is simply the outcome of the competition between these two energies. The low temperatures, the molecules don't have enough kinetic energy to break free, so they stay in the well and forms a liquid or solid. When we heat a substance, we increase its kinetic energy. When that kinetic energy exceeds the depth of the well, the molecules can escape and become a gas. So next, solids, crystals, and thermal expansion. Crystalline solid: a solid material whose atoms, ions, or molecules are arranged in a highly ordered, repeating three-dimensional structure called a crystal lattice. For thermal expansion, the tendency of matter to change its shape, area, or volume in response to a change in temperature at the molecular level of, or it results from the asymmetric shape of the potential well. Crystalline solids molecules vibrate around fixed So, molar mass with a symbol of m, the mass of any molecules of a substance unit grams per mole. So this brings us to the key equation, the molar mass, which you can read right off the periodic table in grams per mole, is simply Avogadro's number multiplied by the mass of a single molecule. This is a powerful tool. If we know the molar mass, we can calculate the mass of a single molecule, or if we somehow knew the mass of a molecule, we could calculate Avogadro's number. Let's see how this works with a concrete sample problem. Find the mass of a single hydrogen atom and a single oxygen. Solution. For hydrogen, molar mass mH is equals to 1.008 grams per mole. mH is equals to mH over Na is equals to 1.008 grams per mole divided by 6.022 times 10 to the power of 23 atoms per mole is equals to mH is equals to 1.67 times 10 to the power of negative 24 grams. For oxygen molecule, molar mass of MO2 is equals to 2 because we have 2 subscript on the oxygen times 10 times 16 rather, because 16 is a molar mass of oxygen is equals to 32.00 grams per mole. Therefore, MO2 is equals to 32.00 grams per mole divided by 6.022 times 10 to the power of 23 molecules per or mole is equals to 5.31 times 10 to the power of 23 grams. Summary: intermolecular forces are electrical and vary with distance, repulsive at short range, attractive at long range, with an equilibrium at um, separation zero, and the potential well. The potential energy curve forms a well. Its depth is the binding energy. Phases of matter determined by the competition between kinetic energy or the temperature and the depth of the potential well. For the thermal expansion arises from the asymmetry of the potential well. Avogadro's number with the symbol of Na 6.022 times 10 to the power of 23 molecules per mole. It is the fundamental bridge connecting the microscopic mass of a molecule to the macroscopic molar mass. Let's We have learned that the properties of matter are governed by electrical forces between molecules. These forces create a potential well whose depth determines how strongly molecules bond. Whether a substance is a solid, liquid, or gas depends on whether its thermal energy is enough to escape that well. Thermal expansion happens because the potential well is not symmetry. And finally, Avogadro's number is the essential tool that connects this microscopic world of molecules to the macroscopic measurements we can make in the lab. Thank you for your attention, and I'm happy to take any questions from everyone.
Assalamualaikum and good day everyone. My name is Guronar Alea and my part of this report is to talk about the kinetic molecular model of an ideal gas. This model helps us understand gases, not by looking at them as a uniform substance, but by looking at the motion of the molecules that make them up. So by studying the movements of these tiny particles, we can explain things we see in real life, like why does a balloon inflate when heated under the sun, why tires get harder after driving, or why does the air pressure changes with altitude. Okay, so the kinetic molecular model is based on several assumptions. So we have four primary postulates, or we can call them assumptions. First, we imagine that a gas contains a very large number of identical molecules. So there are so many molecules that we can talk about their average behavior, which gives us useful predictions about gas behavior. Second, these molecules are treated as point particles, meaning their size is extremely small compared to the distances between them. Think of this like imagining peas floating in a huge gymnasium. The peas are tiny compared to the space around them. The third assumption is that the molecules are in a constant, random motion, meaning they move in all directions, bumping into each other and bouncing off the walls of the container. So, because of this, they hit each other or they hit the walls. And last but not the least is the fourth assumption or the fourth postulate. So it is that the container walls are rigid or fixed, so it cannot be moved. So why does this matter? That's why we need to talk about the next topic, which is the collisions and gas pressure. Gas pressure is actually caused by molecules hitting the walls of the container. So every time that a molecule collides with the wall, it changes direction. And because the momentum is related to velocity, this means that there is change in momentum, which according to Newton's second law, it produces a force. Pressure is simply the total force per unit area exerted by all the molecules hitting the wall. Okay, so for example, imagine blowing up a balloon. So the air molecules inside are moving fast and colliding with the balloon walls constantly. The more molecules there are, or the faster they move, the more they push the walls, and the balloon inflates. This is the same principle behind why car tires feel harder after a long drive. The air inside has been heated by friction, increasing the speed of the molecules and therefore increasing the pressure. Next, we move on to the pressure and molecular kinetic energy. The kinetic molecular model shows a direct connection between the motion of molecules and the macroscopic properties of gases. So we can write this equation for pressure and volume. So PV is equal to 1/3 nm v squared. So let's break this equation down. So first, here the n is the number of molecules, m is the mass of each molecule, and v squared is the average of the squares of the molecular speeds. So where do we use this equation? So this equation tells us that the pressure of the gas depends on how fast the molecules are moving. So it doesn't tells us just how many molecules there are. Okay, so it tells us that gas depends on how fast the molecules are moving. So when we compare this to the ideal gas law, which was discussed earlier, PV is equals to nRT, we find a very important result, and that is the average kinetic energy of a molecule is directly proportional to the temperature. Therefore, we write the average kinetic energy as 3/2 times kT. So here, the K is the Boltzmann constant and T is the absolute temperature. This means that temperature is not just any number on a thermometer. It is actually a measure of how energetically molecules are moving. If you heat a gas, its molecules move faster and collides harder with the walls, increasing the pressure. Next, we will talk about the molecular speeds. So even though molecules have the same kinetic energy at a given temperature, individual molecules have or move at the different speeds. Some are faster and some are slower. And the distribution of these speeds is described by the Maxwell-Boltzmann distribution. And to get a representative speed for molecules in a gas, we use the root mean square speed or VRMS. And VRMS is equal to the square root of 3RT over M. Here, the R is the gas constant, and T is the temperature, and M is for molar mass. So this equation tells us that something very interesting. At the same temperature, lighter molecules move faster than heavier ones. For example, hydrogen molecules move faster than oxygen molecules at the same room temperature. This is why hydrogen gases escape from balloons much faster than oxygen or nitrogen. Also, as temperature rises, the distribution shifts to higher speeds. The molecules move faster overall. Okay, so first let's give an example. Here, what is the average transitional kinetic energy of an ideal gas molecule at 27 degrees Celsius? What is the total random transitional kinetic energy of the molecules in 1 mole of the gas? And C, what is the root mean square speed of oxygen molecules at this temperature? So first, let's identify the setup. This problem involves the transitional kinetic energy of an ideal gas on a per molecule and per mole basis, as well as the root mean square molecular speed VRMS. We are given the temperature of 27 degrees Celsius is equal to 300 Kelvin, and the N is equal to 1 mole. So we use the molecular mass for oxygen. And to determine the average kinetic energy, we will also find the total molecular kinetic energy of the 1 mole. To execute this, first let's solve A. So to solve A, we have 1/2 is equal to m times v squared AB. It is equal to 3/2 times kt is equal to 3/2 times 1.32 times 10 to the power of negative 23 joules per Kelvin, and multiply that to 300 Kelvin. So the total is 6.21 times 10 to the power of negative 21 joules. Okay, let's solve for B. The kinetic energy of 1 mole is KTR is equal to 3/2 nRT is equal to 3/2 times 1 mole times 8.314 joules per mole times Kelvin times 300 Kelvin, and that is equal to 3,740 joules. And lastly, we solve the third one, which is letter C, and we found the mass per molecule M and the molar mass, big letter M, of the molecular oxygen in this example. So we can calculate VRMS in 2 ways. First, VRMS is equal to the square root of RKT over M is equal to the square root of 3 times 1.38 rather, times 10 to the power of negative 23 joules per Kelvin times 300 Kelvin over 5.31 times 10 to the power of negative 26 kilograms. So that is equal to 484 meter per second, and that is equal to 1,740 kilometers per hour. And the second way is the square root of 3RT is equal to molar mass, and that is equal to the square root of 3 times 8.314 joules per mole times Kelvin times 300 Kelvin over 32 times 10 to the power of negative 3 kilograms per mole, and that is equal to 484 meters per second, which has the exact same final answer to the first way. Okay, so finally we will discuss the last portion of my report, which is the collisions between molecules. And like we said earlier, in reality, molecules are not perfect points. They have tiny sizes, and because they move randomly, they collide with each other frequently. And the average distance between a molecule when it travels before hitting another molecule is called a mean free path, and this is denoted by the symbol lambda. So the mean free path depends on 2 main factors. First, the number of molecules per volume. So if the gas is crowded, collisions happen more often, and the mean free path becomes shorter. And the second factor is that the size of the molecules, the bigger molecules collide more often than smaller molecules. But interestingly, the mean free path does not depend on the molecular speed. It mainly depends on how crowded the gas is and how big the molecules are. An example of this is the air at high altitude. The air is thinner, meaning fewer molecules per volume, so the mean free path is longer. Molecules can travel farther without colliding. This affects things like airplane cabin pressure and how quickly gas diffuse. To summarize, the kinetic molecular model gives us a powerful way of understanding gases. The pressure comes from molecular collisions with container walls. Temperature reflects average molecular kinetic energy, and molecules move at different speeds, and this is described by the Maxwell-Boltzmann distribution. And the mean free path tells us how far molecules travel between collisions. So, through this model, we can connect the tiny world of molecules to the larger world we see around us. It helps explain everything from inflating balloons or to why heated air rises or the behavior of gases in engines and the atmosphere. So, thank you so much for listening. Again, my name is Nor Aliyah Guro.
Assalamualaikum and good day to everyone. This is Hanifa Ismail Makagar, and the next topic we will be discussed is about the heat capacity. First, let's understand the basic idea of heat capacity. Heat is a form of energy that is transferred from one object to another due to a temperature difference. When heat is added to a substance, the energy of its molecule increases. As the molecule energy increases, the motion of the molecules becomes faster, which results in an increase in temperature. However, different substances require different amounts of heat to increase their temperature. Some substances need more heat while others need less heat for the same temperature change. This property is called heat capacity. More specifically, the molar heat capacity at constant volume, denoted as CV, it is defined as the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin while the volume remains constant. When we use the molar heat capacity at the constant volume, the volume of the gas is kept fixed. This means that the gas is contained in a rigid container and cannot expand. Because of the gas cannot expand, it does not do work on its surrounding. As a result, all the heat added to the gas goes entirely into increasing the internal energy of the molecules. And this increase in internal energy causes the molecules to move faster, which raises the temperatures of the gas. Because of this, the heat added to the system is directly related to temperature change through the equation dQ is equals to N times CV times dT, where dQ is the heat added, N is the number of moles, CV is the molar heat capacity at a constant volume, and dT is the change in temperature. This equation shows that the heat added to a substance depends on the 3 factors: the amount of substance, the heat capacity, and the change in temperatures. But the question is, why do different substances have a different heat capacity? To answer this question we need to introduce the concept of degrees of freedom. Degrees of freedom refers to the number of independent ways that a molecule can move and store energy. In other words, it describes how the molecules are able to move and how the energy is distributed among those motions. So there are 3 main types of molecular motions. The first is the translational motion, which refers to the movement of the molecules from one place to another. These molecules can move in 3 directions, along the X, Y, and the Z axis. Because of this motion contributes to the 3 degrees of freedoms. The second type of motion is rotational motion, which refers to the spinning of the molecules about their center. This motion gives 2 degrees of freedom. The third type of motion is vibrational motion, which occurs mainly in solid. In solids, atoms are fixed in position, but they vibrate back and forth about their equilibrium positions. And these vibrations occurs in 3 directions. Because of the nature of the vibration, each direction contributes 2 ways of storing the energy. As a result, solids have 6 degrees of freedom. To relate these motions to heat capacity, we use the equipartition of energy principle. This principle states that energy is equally distributed among all the available degrees of freedom. According to this principle, each degree of freedom contributes to 1/2 times R to the molar heat capacity. Here, R is the universal gas constant, which has the value of 8.314 joules per mole times Kelvin. Using these principles, the molar heat capacity can be expressed as Cv is equals to F divided 2 times R, where F represents the number of degrees of freedom. Example, a monatomic gas such as the helium has only transitional motion. Therefore, it has a 3 degrees of freedom, giving Cv is equals to 3 over half times R. A diatomic gas such as the oxygen has a 3 transitional degrees of freedom and 2 rotational degrees of freedom for a total of 5. This gives Cv is equals to 5 over half times R. In the case of solid, atoms vibrate in place and effectively have a 6 degrees of freedom. So substitute F is equals to 6 divide 2 is equals to 3. So Cv is equals to 3 times R. This result is known as the Dulong-Petite rule, which states that the molar heat capacity of the most solid elements is approximately equal to 3R.
Now, let us consider an example to apply the heat capacity. Consider 2.50 moles of oxygen gas, which is a diatomic gas. The temperature increased by 50 Kelvin at a constant volume. Find the heat added. So from the given, we have N equals to 2.50 moles, and the change in temperature is 50 Kelvin. Since the volume is constant, we use the heat capacity equation dQ is equals to N times Cv times dt. Because the gas is diatomic, we use the Cv is equals to 5 over 2 times R. Substitute the value of R, we can get Cv is equals to 20.785 joules per mole Kelvin. Substitute into the equations we have, dQ is equals to 2.50 times 20.785 times 50. This gives dQ is equals to 2,598 joules, or approximately of 2.60 times 10 to the power of 3 joules.
Conclusion, heat capacity describes the amount of heat required to change the temperature of a substance. At a constant volume, the heat added to a system is directly related to the temperature change through the equation dQ is equals to N times Cv times dt. The value of the molar heat capacity depends on the ways of the molecule can store energy, which are described by their degrees of freedom. As a result, different substances such as the monoatomic gases, diatomic gases, and solids have a different heat capacities.
Assalamualaikum. Greetings, peace, good day. I am Nasim Chipindaton, the last reporter of this group. I will be discussing the molecular speed and the phases of matter. Starting with the molecular speed, we are going to find out and discuss how it is being measured, and we are also going to discuss the Maxwell-Boltzmann distribution. So make sure to listen carefully so that you will be able to catch up and follow with this discussion. What is molecular speed? Molecular speed refers to how fast a gas molecules or particles move. Basically, it is the distance traveled by a particle or molecule over time. In the diagram, molecular speed is represented by the letter V. I know that you are already familiar with this formula. We have x is equals to Vt, which is distance is equals to speed multiplied by time. These are concepts that are already discussed when we were in high school. And in college, we are going to find out more about these topics. So I do hope that you will continue listening in this discussion because we have plenty of more to discuss. Moving on, we are going to look at in this figure. So I want you to listen carefully. Now we have this experimental setup of molecular speed. To measure molecular speed, scientists use an experiment using rotating disks. Now, I know that some of you are already flabbergasted and are overwhelmed by the structure, but I will explain this carefully and step by step. First, a substance was heated, producing gas molecule. These gas molecules pass through into a small hole into the vacuum chamber. It then passes through into a small hole and then it forms a narrow beam. Now here comes the two rotating discs. As you can see, this rotating disc helps us identify which gas molecules can enter correctly. Now, only the gas molecules with the correct speed can enter both these. What does this mean? It means that if the gas molecules moves too slow, then it will be blocked. But if the gas molecules moves too fast, then it will miss. But if the gas molecules moves at the correct speed, then it will pass through. This is how they are able to measure molecular speed. And this is just simply an explanation of the experimental setup. Now I'm sure that most of you noticed that the molecule was able to pass through because it matches the speed of the object. Now I will be showing you the equation in order to solve for this kind of setup. This is the equation. We have V is equals to W multiplied by X over theta. Now let's break it down step by step. First is we have the V. V refers to the speed of the molecule. Next is we have the W, and that is the omega. Omega refers to how fast the rotating disk is. Next is we have the X. It is the distance of the rotating disk. And last, we have the theta. It refers to the angles of the rotating disk in which where it rotates. Now, people use this formula in order to calculate and solve for the speed of molecule based on timing and rotation. Now you might be wondering what will happen next. When the molecule passes through the rotating disk, it will breach the detector. Then, the scientists will be able to count how many molecules pass through at different speed. This leads us to the use of the Maxwell-Boltzmann distribution. And now we are going to focus on this next topic. But before that, I want everyone listening in this video to take a deep breath first before we continue to the next topic. Let us have a short moment of rest. Let us inhale and exhale. Again, inhale, exhale. Thank you so much, everyone. Now we are ready to continue the next part of our topic, the Maxwell-Boltzmann distribution. Have you ever wondered why other particles are moving very fast while others move slowly even at the same temperature? Well, brace yourself because we are going to discuss the Maxwell-Boltzmann distribution. This will help us understand and explain that particles move at different speeds. Now, what is the Maxwell-Boltzmann distribution? The Maxwell-Boltzmann distribution is a concept in chemistry and physics that helps us show the speed of gas particles distributed at a certain temperature. This means that not all particles move at the same speed. Some move slowly, some move very fast, and most move at an average speed. In order for you to understand better about the Maxwell-Boltzmann distribution, let's take a look at this graph. As you can see, we have the x-axis and the y-axis. The x-axis refers to the speed of particles, while the y-axis refers to the number of particles. As you can see, the peak of the curves shows the most probable speed. What is the probable speed? The probable speed is the speed that most particles have. Now I will show you the equation of the Maxwell-Boltzmann distribution. Now this is the equation of the Maxwell-Boltzmann distribution. But don't fret because we are not actually going to have a solving on it. I am merely showing you the equation so that you will have an idea of how the Maxwell-Boltzmann distribution works. This is the temperature. Temperature also plays a significant role when it comes to the speed of particles. When temperature increases, the particles also moves very fast. The curve becomes wider, the peak becomes lower. When temperature is high, particles move very fast. In other words, heat gives energy, so particles also moves fast. That's how temperature also plays a significant role in the speed of the particle. Let's have a real life example. Imagine we have a student named Anastasia. She was planning to cook dinner, and it was her first time. So, what she did first was boil water because she is planning to cook spaghetti. Now, when she was boiling the water, she saw a fog letting out of the pot. Now, what does this mean? This happened because temperature is high, so particles move very fast. And what happened is a process of evaporation. Another example is when you are using perfume. When you apply perfume in a warm and secluded area, it will spread faster if the room is at a high temperature. It is because when temperature increases, particles also move very fast. So when you use perfume in a cold area, then your perfume will not be smelled by those people at farther places because it will not be able to move at a very fast speed. This is how very important temperature plays a significant role when it comes to the speed of a particle. The Maxwell-Boltzmann distribution equation helps us understand that the number of molecules also depends on their speed, mass, and temperature. We also have the energy form of this equation. This equation can also be written in terms of energy. This is the equation. As you can see, this explains that molecular motion can also be explained using kinetic energy. Next, we have the equation for the most probable speed. Here is the equation. This is the speed that most molecules have. This means that when temperature increases, speed also increases. Next, we have the average speed. Here is the equation. This equation represents the average of all molecular speed. And last, we have the RMS speed. Here is the equation. The speed gives more importance to molecules who moves faster. Now let us compare these three speeds. The most probable speed is less than average speed. Average speed is less than RMS speed. This equation shows that higher temperature results to molecules moving faster. Lighter molecules means that molecules move faster and heavier molecules move slower. Now we understand molecular speed. Moving on, let us proceed to our next topic, and that is how matter changes between solid, liquid, and gas. We have three main phases of matter. First, we have the solid. Second is the liquid, and the third is the gas. In gas, molecules move freely and the interactions are weak. However, in liquid and solid, the interactions are strong. Particularly in solid, the particles are rigid and compact. This means the particles are close to each other. Because of these interactions, this what allows us to understand the structures of matters and atoms around us. Now we are going to proceed to the next part of our discussion, and this is the last topic. This is all about the phases of matter. We have the solid, liquid, and gas. We are going to learn the interactions between these three. First, we are going to identify their molecules. In gases, their molecules are moving freely and the interactions are weak. However, in solid and liquid, their interactions are strong, particularly solid. This what allows matters to stay close together and form new structures. Why do phases changes? Haven't you ever wondered about it? Of course, some of you have already wondered how does it change? We are going to find out about that. The reason for that is because the temperature and pressure plays a role in the behavior of the molecule. If you increase the temperature, the molecules move faster. If you increase the pressure, the molecules are pushed closer together. Because of this, matters can change into different phases. Like for example, we have a solid to liquid, so it turns into the process of melting. Next is we have the liquid to gas, so it causes vaporization. We also have solid directly to gas, and we have the process of sublimation. Because of the factors like temperatures and pressure, it causes different phases to these different molecules. That's how phases changes when it comes to matter. To better understand the phases of matter, scientists uses a phase diagram. What is the phase diagram? The phase diagram shows how temperature and pressure determines the state of the substance. The vertical axis is the pressure and the horizontal axis is the temperature. Each region shows what materials are they. We have the solid, the liquid, and the gas. Moving on, we have what we call the phase boundaries. These are lines formed between different regions. This means that two phases can exist together. I repeat, this is what we call the phase boundaries. Now, class, I want you to take note of these two very important points in the phase diagram. We have the triple point and the critical point. What is the triple point first? The triple point is a condition where solid, liquid, and gas all exist at the same time in an equilibrium. It means that solid, liquid, and gas exist all together at the same time. So how about critical point? So critical point is a condition where liquid and gas become indistinguishable. It only involves liquid and gas, and it creates a supercritical liquid. Now, basically, liquid becomes one with gas. That's the critical point. Unlike triple point, the solid, liquid, and gas exist all together at the same time. Now, let's take a look back again at the graph. As you can see, there are lines on it. These are what we call the phase curve. We have the fusion curve, we also have the vaporization curve, and the sublimation curve. The fusion curve is the phase line in which the solid becomes liquid, while the vaporization curve shows how liquid turns to gas, and The sublimation curves shows how solid turns to gas. Temperatures plays a significant factors on molecular energy. As temperature increases, more molecules gain enough energy to change phase. Because of this, some substances melt, boil, or evaporate at a faster rate during a specific temperature. In summary, this temperature and pressure control phase changes. And phase changes also depends on molecular interactions. That is why we have the phase diagram. It allows us to better conceptualize how these phases and interactions happen. And finally, we are done to the last part of our discussion, the PBT surface. First, let's break that name down. What does P represent? So it represents pressure, B represents volume, and T represents temperature. So basically, the PBT surface represents the connection between the pressure, the volume, and the temperature. Now, each point on this line or graph actually shows the actual state of the substance. So we have the solid, liquid, and gas. So I want you to take note of the key important parts because this might get a little bit hectic, but I'm sure you will be able to catch up. Now let's try to understand this graph. Now I want you to look carefully on this picture. So as you can see, we have solid, liquid, and gas. So if we try to look carefully, we have one direction changes the temperature while the other one changes the volume, and the height changes the pressure. So in this graph, it basically shows these three things. So it's very helpful when you are actually trying to discuss the changes that happens in matter. So we can actually create special lines in this PVT surface. First, we have the isotherm. So the isotherm shows the amount of constant temperature. Next is we have the isobar. It shows the constant pressure. And last is we have the isochores. It shows the constant amount of volume. Now, what does this indicate? This line helps us understand what happens when we keep one thing constant. So class, are you still following? Because if you do, then we are going to follow a path on this surface. Now, if we try to look again in the figure, heating at constant pressure can turn to melting and then boiling. In addition to this, compressing a constant temperature can cause gas into liquid. So in simple terms, this 3D graph actually shows us how substance change step by step. In conclusion, the speed of molecules explain how different phases of matters happen. We have solid, liquid, and gas. Additionally, temperature also affects the molecular speed. Understanding these key concepts helps us understand everyday lives, like how melting and boiling, and of course, evaporation happens. Overall, studying thermal concepts allows us to understand how heat affects matter. And using this knowledge, we are able to explain everyday aspects in our lives. That would be all. Thank you so much. I am Nasim G. Pindaton, and we are deeply grateful for you to listen in our report. Thank you and goodbye.